Hey guys, it's time for a video on section 14.2, inference for relationships. So when we're talking about relationships, we're talking about two-way tables. That's where we're going to have to start this lecture, two-way tables. We have to remind ourselves how two-way tables work and how do you read them? And more importantly, how do you write them? Like how do you set up the two-way table? Which variable goes in the rows? Which variable goes in the columns? All right, here we go. So we're going to learn all of these things, how to compute expected counts, conditional distributions, and contributions to the chi-square test statistic. Okay, that's all going to be at the beginning. That's going to be with your two-way table. You're going to check the three conditions: random, large sample size, and independent condition. Okay, and this large sample size, we're just going to call that expected counts. Okay, because that's really what you're counting. That's really what you're looking at with the large sample size condition. So we're going to call that random, expected counts, and independent. Those are the three conditions. Then we're going to go ahead and perform a chi-square test for homogeneity. And what does that mean? Homogeneous means the same, right? So we're going to look at two different populations, okay, or two different treatments and see, is the distribution of the categorical variable the same among those two or even more populations or treatment groups? Then we're also going to learn, later we're going to learn the chi-square test of association. And it's called association slash independence because independence is the opposite of association. I'm just going to stick with association, not to confuse you. Okay. And we want to look at, is there an association within one, okay, population? Is there an association? Okay. And so there again, if you think back all the way back to chapter 2, we learned about bivariate data and we learned to look at two-way tables, and we learned what it means if there's actually an association or if there's not an association, right? It means if the distribution is the same, that means there's no relationship, no association. Okay. And then finally, we're going to examine individual components of the chi-square test statistic as the FU analysis. Yes, you heard that right. I'm calling it the FU analysis. And then lastly, we're going to interpret computer output. Computer output is so nice, especially Minitab output, because all your calculations are right there, right in front of you. And it's even labeled. It's almost impossible to get it wrong when you have Minitab output. Okay. Okay, so let's get started with two-way tables. Okay, so two-way tables have a lot of uses. And in this section, we're going to start by developing a test to determine whether the distribution of a categorical variable is the same for each of several populations. And that's your test of homogeneity. Then we'll examine a related test to see whether there's an association between the row and the column variables within a two-way table. And that is your test, chi-square test of association. Okay, so those are the two tests that we're going to look at. But we have to remember how two-way tables work. So with two-way tables, you have two variables. You have a row variable and a column variable. And this is critically important, okay? Write this in your notes. The explanatory variable goes in the columns. The explanatory variable is the column variable. Make sure you write that in your notes. That's super important because sometimes they're not going to provide you with the table. They're just going to provide you with the counts and you have to set up the table. Okay. So remember that when you're setting up a table or when you're reading a table, the explanatory variable is right here, the column variable. So in this case, in this example, and this example is in our textbook, the type of music that is playing is the explanatory variable. The response variable is your row variable. And these are the types of wine, the types of wine. Okay. So there's French wine, Italian wine, and other wine. So wine that's, not French and not Italian. So maybe Spanish, maybe American, whatever, right? Anything that's not French or Italian. So market researchers suspect that background music may affect the mood and buying behavior of consumers. So one study in a supermarket compared three, and in our textbook, we find out that this actually was a study in Ireland, right? Which I thought that was interesting. But one study in a supermarket compared three randomly assigned treatments: no music, French accordion music, and Italian string music. So that's these column variables, those are the treatments. So those are your explanatory variables. Playing no music, playing French music, and playing Italian music in the wine store or the supermarket, right? And we want to know, does the type of music that you're playing impact the buying behavior of these wine shoppers, right? So here's a table that summarizes the data. Okay. So here's our problem. Let's calculate the conditional distribution in proportions. Okay, so 0.03, 0.10, whatever, right? So there's decimals of the type of wine sold for each treatment. Okay, so remember where the conditional distributions are. Those are within this column, right? So holding the treatment the same. Okay, so that would be these 30, 11, and 43. Then this treatment, you have 39, 1, and 35. So you're just turning these into percentages. So the conditionals are inside the table, right? Then the marginals are the ones in the margin or outside the table, okay? Make an appropriate graph for comparing the conditional distributions in part A. So the appropriate graph that we're going to use is a side-by-side comparative bar graph, okay? Because remember, categorical data, bar graphs, not histograms, but bar graphs. Part C, are the distributions of wine purchases under the three music treatments similar or different? Give appropriate evidence for parts A and B to support your answer. So we're not doing any inference yet. We're not doing any, state plan do conclude. We're just doing some review of, hey, how do we read two-way tables? Okay. So here's all your data. So let's go ahead and first figure out the conditional distributions. Okay, the conditional distributions. Okay, so when there's no music playing, so that's in this column, so that's the 30, 11, and 43. Okay, when no music is playing, here's your conditional distributions. Well, 30 out of 84, 11 out of 84, and 43 out of 84. Okay, so that would be about 35.7% or 0.357, 0.131, and 0.512. Okay, so that is the conditional distribution under the condition that no music is being played. Okay, and then under the condition of French music being played, or under that treatment, then you have 39 out of 75, 1 out of 75, 35 out of 75. Okay, so those are these calculations right here. So 0.52, 0.013, 0.467. Then when you play Italian music, okay, 30 out of 84, 19 out of 84, 35 out of 84. Okay, so that's 0.357, 0.226, 0.417. Okay, so there's your conditional distributions. Now let's graph these and visually take a look at them, and you'll see it'll be very striking when you graph it. Okay, boom, what do you see? So here's the conditional distribution when there's no music being played. Here's the percentage of French wine being sold, about 35.7%, Italian wine being sold, and then other wines being sold, a little over 50%, right? Now, when French music is being played, check this out. The French goes from 35, boom, all the way past 50. But look at what happened to the Italian. It went from, what was this, 14 or so, something like that, all the way down to like 1% or something really low, right? Then when you play Italian music, well, boom, the Italian wine sales go way up, French comes back down. Okay, interesting. Okay. So what's the biggest difference that you see immediately that's visually like perceptible? Well, obviously the Italian wine, okay? And then look at the French one, the French wine sales when French music is being played. Wow, it really is pretty high, right? Okay, so when you're doing a chi-square test and when you're calculating the chi-square test statistic, the problem is that you're doing many comparisons all at once, okay? And so here's a couple points to keep in mind. An overall test, okay, so statistical methods for dealing with multiple comparisons usually have two parts. The first part is an overall test to see if there's evidence of any differences among the parameters, and then a detailed follow-up analysis. If there are statistically significant differences, then you're going to do the FU analysis, right? The follow-up analysis. Okay, but that's after you do the overall test to see if there's statistically significant differences. Okay, if there's minor differences that could just happen from random chance alone, we don't deal with the FU analysis. We don't need a follow-up analysis. Okay, so the follow-up analysis is only performed when you have statistically significant results. Okay. So what's the overall test? Well, the overall test is called the chi-square test of homogeneity. Okay. So your null hypothesis in words, and this is not how you're going to write your null and alternative. You're not going to use words, but this is to explain to you what the null and alternative are saying. So you understand conceptually what the null and alternative really are. Okay, but you're not going to write these like this. Okay, but your null is always a statement that there's no difference in the distributions of the categorical variable for those several different populations. So in other words, yes, homogeneous. Okay, no difference. Okay, not heterogeneous or heterogeneous. I don't know. How do you say that? Okay, the alternative is there is a difference. Okay, again, this is not how you're going to be writing these, but that's conceptually what they're saying. Okay. So we compare the observed counts in the two-way table with the counts we would expect if H null were true. Because remember, our assumption, we always lead with, let's assume that H null is true. If H null is true, what would the expected counts be? Not the expected proportions, but the expected counts. So you have to get the expected proportions first, and then obviously multiply the expected proportions by n, right? Okay, so what would we expect? Well, the overall proportion of French wine bought during the study was 99 out of 240, or 40.7%. Okay, so the expected counts of wine should be about 40.7%, right? So where are they getting this 40.7%? Well, they're looking at the totals. They're looking at the total. So there's 99 out of 243. 243 is the total. Okay, so let's go back a couple slides to the actual distribution. Okay, 243 is the total. And then 99 is the row total. So out of all of the bottles of wine that were sold, regardless of music, right? Whether there's no music, French music, or regardless of music, what's the row total? What's the total of French wines sold? 99 bottles out of 243. So for the entire marginal distribution, you have 40.7% of the bottles of wine were French bottles of wine. Okay. Then do the same thing for Italian and the same thing for others. So 31 out of 243, okay, was Italian wines that were sold. 113 out of 243. So you're getting these row marginal distribution of the row variables, right? Okay. And so what you're doing is now you're applying this 40.7% to these totals, which are the column totals. Okay. So you're going to do row total divided by column total times, or sorry, row total divided by total, and then multiply that by the column total. Okay. Okay. And then you're going to do that for all three of these. Okay. Marginal distributions. Okay. All right. So if you generalize this formula, what we've done is we've taken, okay, what we've done is we've simply just taken, and I apologize for the quality of the slide is not very good. Okay, but here it is right here. Your expected counts, okay, is row total times column total divided by the table total. And really what we did was we did row total divided by table total, or I call this total. So row total divided by total times column total, but that's mathematically the same as this. That's the same as row total times column total divided by total. Okay. But conceptually, it's easier to understand if you look at the marginal distribution of the row, then you apply that to this column total. Okay, so how do you calculate the chi-square test statistic? Well, after you get all the expected counts and you have the observed counts, right? The observed counts are what are actually in the cells already. Okay, the chi-square test statistic is just simply equal to the standardized, it's like the standard deviation, right? It's the observed minus the expected quantity squared divided by the expected. Okay, so chi-squared is equal to sigma. So this would be chi, looks like a capital X, okay, but it's the Greek capital letter chi. So chi-square is equal to sigma, which is just the summation sign, capital sigma, okay, summation of the observed minus the expected quantity squared over expected. Okay, so you do this for each one of the cells in your two-way table. So each one of those cells is going to have an observed count, an expected count, and then this contribution to the chi-square test statistic. Okay, so you're going to calculate that for each one of the cells. Okay, the inside cells, not the total, not the marginals, okay, but the inside cells. So here we go. So here's the table again, right? So this is the observed, these are all the observed counts. Observed means the actual, like what actually occurred. Okay, how do we get the expected counts? So do 99 times 84, so row total times column total divided by total, okay? That will give you the expected counts. Okay, that will give you the expected counts. So here are now the expected counts for all 9 of those cells. Okay, notice that expected counts do not have to be integers. Expected counts is perfectly fine for it to be 34.22. Now, can you sell 0.22 of a bottle of wine? No, you can't, but that's okay. These are expected counts. Okay, expected. Then for each one of these, now you can calculate the contribution to the chi-square test statistic. So here's 30, that's the observed, minus 34.22. So obviously you get a negative number, negative 4.22, but then you square that and then divide it by the expected. So that gives you 0.52. So that's the amount that this particular cell contributed to the chi-square test statistic. You do that for each one of these 9. Okay, and you get a total, then you add all those contributions together and you get a total chi-square statistic. Okay, so that's how you get the chi-square test statistic. Let me go back to that if you want to write that down. So this would be chi-squared is equal to sigma of observed minus expected quantity squared over expected. Okay, let me pause the video and go ahead and take a look at that. Is it going to let me pause?